we have learned to translate between a system of equations and an augmented matrix. So let's see, what can we do with a matrix? Well, the better question is, what can we do with a system of equations? Well, I have an example here, and I propose that we can do three different things with a system of equations, right? With this system, it is possible to interchange the two equations, right? If I have the system x minus y is equal to 4, and then 3x plus 2y is equal to minus 1, those are the same system, right? I still need to solve the same two equations. Okay, so I can interchange two equations. I can also take an equation and multiply a single equation by a non-zero constant. So I could say, okay, take equation 2 and multiply it by 3. Okay, and if I do that, I get the system 3x plus 2y is equal to minus 1. Haven't changed the first one, but then I would have 3x minus 3y is equal to 12. Okay, effectively in as a result of this, I have the same system because I can take that same equation and if I were to divide both sides by 3, it's the same thing. Okay, so this is also a valid operation on an equation, or on a system of equations. And last one, we can say we can add a non-zero multiple of one equation to another. This is the idea of elimination by addition, okay, which we saw before. So I can say I want to take and I want to add 3. I can take row or equation 1 and add to it -3 of equation 2 and put that into equation 2. So my first equation won't change. 3x plus 2y is equal to minus 1. And then when I multiply the second equation by 3 and add it, or -3 and add it, the x's would eliminate, and I'd have 5y is equal to, oh, let's see, I need to take -3 times -3 times 4 is 12, and then add that to minus 1, minus 13. Okay, so I can still do that, and that allows me to solve the system, right? So since a matrix is really just a different form of the system of equations, these three operations on systems of equations translate to a matrix context as well. And these are the three elementary row operations we're going to be using over and over and over. So we can interchange two rows of a matrix, we can multiply any row by a non-zero constant, and we can add a non-zero multiple of the row. Okay, now the only thing that I will caution you on is that both the text and myself, and eventually you, will be illustrating each one of these row properties using symbols. Okay, so the notation here is going to be extremely critical, and pay close attention to the symbols used. Okay, so here's our example. A matrix is given, and then it says perform the operations below. Okay, and these symbols here are indicating what elementary row operations we need to use. Okay, so for the first one, when we have R1 double arrow R2, if you can imagine, that's double arrows going both ways, so that means interchange. Okay, so for part A, what we're going to do is take the first two rows and swap them. Okay, so for A, our matrix is going to be, okay, third row is going to stay untouched. 2, 0, 3, 8. Okay, and I'm going to use a bracket because that's what the book uses. And I'm going to switch row 1 and 2. So row 1 is now 1, 4, -1, 9. And the second row is 4, 3, 0, 5. Okay, so that's all there is to performing this single row operation. Okay, for part B, okay, this says take 3 of row 2 as it currently is presented, okay, and put it into row 2. So if you need to, just kind of make a little note to yourself like what that is. That's going to be this row is going to now be 3, 12, negative 3, and then 27. Okay, so then in your new matrix, you're going to leave rows 1 and 3 alone. And instead, you're just going to write this new row in that is 3 times the original one. So 3, 12, minus 3, and 27. Okay. Now, the last one is perhaps the most complex because you either need to write stuff down extra or hold a lot of numbers in your head. Okay, so this one is where we illustrate the third elementary row operation of adding a multiple of one row to another. So what this says is I need to take row 1, subtract 4 of row 2, or equivalently you can say add negative 4 times row 2 and put it into row 2. Okay, so if we think about the final outcome, row 1 and 3 are going to be unchanged. So I'm just going to reflect that here. 4, 3, 0, 5, 2, 0, 3, minus 8. Okay, now for row 2, you can either go off to the side and do the math independently. So you can say, okay, row 1 is 4, 3, 0, 5, and then you're going to add to it negative 4 times row 2, so plus, and then take row 2 times negative 4, negative 16, 4, and then minus 36. Add that, so you get 0, minus 13, 4, and minus 20, or minus 31. Okay, and that's going to go here. Minus 13, 4, minus 31. Now, this little bit of work that I did over here, right? I wanted to put that in red. This little bit of work over here on the right, you don't need to do. Okay, if you can kind of do it step by step in your head and hold that all in your head, please do. I do that, but be careful. You can make mistakes. I do. Okay, and you'll probably see me in the video mess up a time or two. Okay, but I'll be sure to correct it. All right, but the main idea here now is that we have our augmented matrix. We can translate from a system of equations to an augmented matrix, and we know some things that we can do with the augmented matrix once we have it.